Welcome back to another discussion on fiber optics. In the last lecture, we discussed that we can classify fiber based on refractive index profile, and we saw that based on refractive index profile, there are two kinds of fiber termed as step index fiber and gradient index fiber. For step index fiber, we saw that the refractive index of core and clad are kept constant, whereas in gradient index fiber, the refractive index of core varies with the distance from the core axis, whereas the refractive index of clad we have taken as constant. And then we drew the profiles of the two kinds of fiber, and we saw that how the profile looks like. Now we are going to discuss another classification of fibers based on modes. Now, the first question which comes to our mind is, what are modes? Fiber optics actually is a full-fledged subject, but here, because I am giving you a very brief introduction of fiber optics, so I'll just give you in brief the explanation of what are modes. So, you all know that light is an electromagnetic wave. Which satisfies Maxwell equations. Which satisfy Maxwell equations. These Maxwell equations you might have learned in electromagnetic theory, or in my further lectures we'll discuss. These are Maxwell equations. These are differential equations. Now, when I apply boundary conditions to these Maxwell equations, now what can be our boundary conditions for an optical fiber? For example, the refractive index profile we can take as a boundary condition, that for the core, how is the refractive index, for the clad, how is the refractive index. Then after applying these boundary conditions to the differential equations, we can solve the differential equations and we get the different solutions. The different solutions of these differential equations are known as modes. Of these equations after applying boundary conditions. Now I'm telling you very qualitatively. I'm not going into any technical details. I'm just giving you a very basic idea of what are modes. Equations are known as, we can do in detail in further lectures, as modes. So basically, each mode is characterized by a discrete angle of propagation. So, different modes are being guided inside the fiber and they travel at different angles. Now here I would like to tell you the basic waveguide parameter. The waveguide. So we can derive all these, but here I am just giving you a brief idea. The waveguide parameter is given by V 2 pi lambda naught, where lambda naught is the wavelength of light in free space, a the radius of the fiber, n1 square minus n2 square to the power half. This is a numerical aperture. And number of modes n is given as q upon 2 into 2 plus q v square. So basically what I'm trying to say here, tell you here, is that number of modes, that first of all each mode is characterized by a discrete angle of propagation. So at different angles different modes will travel inside the optical fiber, and there is some waveguide parameter which depends upon the thickness of the fiber, that is a, where a is the radius of the fiber. n1 and 2 you all know that are refractive index of core and clad, and number of modes, it depends upon this parameter v, which in turn depends upon a. So the basically what I want to tell you is that number of modes, it's directly proportional to thickness of the fiber a. This is the only thing which I am trying to tell you. So for example, for q is equal to 2, v is equal to 10, number of modes n, there are approximately 25 modes. Don't worry about all these parameters. Just the basic thing is that light, which satisfies Maxwell equations, which are differential equations, and when we apply the boundary conditions we get the solution of these differential equations, and these solutions are the modes of the fiber, and each mode is characterized by discrete angle of propagation, and the number of modes, it depends upon the thickness of the fiber. So based on this we can say that if the thickness of the fiber is less, we have less number of modes, and if the thickness is more, we have more number of modes. So based on this fact, we can classify fiber as single mode and multimode. So based on the number of modes, my classification is, first is single mode fiber. The fiber, when the fiber has only one mode, it is termed as single mode fiber, and the light travels, and here the light travels along the axis. And this kind of fiber is very difficult to fabricate. So typical diameter of core here varies from 8 micrometer to 12 micrometers, and diameter of clad, these are just typical numbers. And another classification based on this is, second is multimode fiber, which supports large number of modes, and obviously I already told you number of modes depends upon the thickness of the fiber. So for a multimode fiber we need thick fiber, multimode fiber, which supports large number of modes. And different modes, they reach the other end of the fiber in different time, because the different modes will have different optical path inside the fiber, so they will reach in different, so due to which there will be time delay in the pulse, which is referred to as pulse dispersion in different times, causing time delay. This is referred as pulse dispersion. When different modes, they travel with different time inside the fiber, so there is a time delay in the signal, and this is referred as pulse dispersion. Now, how can we minimize this dispersion and what kind of fibers are advantageous? We'll try to see in the next lecture. Thank you.